Dear students, in this video, we are going to discuss various parameters where what are the things that comes while you are discussing the microstrip antennas. Okay, so let us see one by one. Let us see one by one. So the first one is return loss. Okay, so the very important parameter. The first one is return loss. Okay, let us see what is meant by this return loss. For example, let us take our antenna. So consider this is my antenna. Okay, so this is my antenna. Okay, so let us consider this is port 1 and this is port 2. Okay. So, for example, let us consider here I have provided power. Okay, what is the main function of an antenna? Whatever the input power you have provided, for example, let us consider PI. PI denotes my input power. PI denotes my input power. So, if PI is my input power, PI is my input power. Okay, so I have transmitted this at port 1. Okay, at port 2, what should happen? Whatever the power you have provided, all should get radiated. If it is an ideal, this is in the case of ideal, means 100% of input power should radiate into the free space. That is ideal case. But no antenna or no person in the universe is ideal. Okay, so there will be some opposition or there will be some impedance mismatch. So what happened, for example, if I have provided PI, okay, some of the power is transmitted. Some of the power is transmitted. Some of the power is transmitted. And due to some impedance mismatch, some of the power will get reflected back. Some of the power will get reflected back. Okay, some of the power will get reflected back. Okay, so here see, for example, if I provided PI, okay, let us consider 50% of the PI. 50% of the PA is radiated or transmitted, and due to some impedance mismatch, let us consider 50% of the power is reflected. Okay, so here PI denotes the incident power, PI denotes the incident power, PT denotes the radiated or transmitted power, and PR is reflected power. Okay, so reflected power. So means here you are providing input at port 1, the reflected power is also getting at port 1. So here the return loss, it is denoted with S parameter. We are calling it as S11. So means we are providing input at port 1. Okay, so how much of the power is reflected back at the same port 1, S11. So it is the ratio of input power to the reflected power. A return loss is defined as the ratio of input power to the reflected power. So for example, when will we consider it is a good system? So for example, when will you consider it is a good system? For example, if I transmitted PI, means if PI, if you consider it as a PI, if 90% of the power, 90% of the whatever the input power you have provided, if it is transmitted or radiated, and only 10%, only 10% is reflected, this case is considered. 10% means that is nothing but 0.1 PI is reflected back. How much is radiated into the free space? That is 0.9 PI. What is the total power? Total power is 1 PI. So it is getting divided into total power 1 PI. So 1 PI is divided into 0.9 PI, that is radiated, plus 0.1 PI, that is reflected back. Okay, then we call that system is a good system. That antenna is a means in this case at that frequency, okay, we can consider it as a reference level, or it is acceptable. Okay. What do you think? Or the still better one? So if 0.94 is transmitted or radiated, and if 0.94 means 0.06 is reflected back, that is for the good one. What is the still better one? 0.096 is radiated or transmitted. Okay, and only 0.04 is reflected back. Okay, that is the good system. Okay, so based on this, okay, so if you observe here, okay, so let us see here in this diagram, very important one. So return loss, it is the loss of the power in the signal written or reflected by the discontinuity in the transmission line of optical cable. So this discontinuity can be a match with the terminating load with the discontinuity. It is expressed in this dB. So what are the units of return loss? dB. Okay, so here I have provided the input power. So some of the power is get transmitted or radiated, and due to some impedance mismatch, some of the power is getting. So you are providing input at port 1, and the same reflected power is also getting at port 1. So the return loss, we can call it as S11. So it is minus 10 log base 10 Pi by PR. So if you substitute here Pi by, for example, what is the acceptable one? 90% is radiated, only 10% is 10% means I can call it as 0.1 Pi. Okay, so 0.1 means I can write it as 1 by 10. So if I write 1 by 10, Pi will get cancel, I will get minus 10 dB. So this is the acceptable one. So S11 dB, this is the acceptable one. Okay, means you will get to understand when what is this in the graph. Okay, so let us look at the graph. Okay, so for example, let us see here this graph. So this graph is this graph is between the frequency versus S11 in dB. So S11 means nothing but a return loss. S11 means nothing but a return loss. Okay, so here minus 10 dB line. I have already told minus 10 dB line is the threshold. Minus 10 dB line is the threshold. Minus 10 dB line, minus 10 dB line is the threshold. Minus 10 dB line is the threshold. Okay, so in this minus 10 dB line, minus 10 dB line. Okay, so what happen if it is minus 7, or what happen it is minus 3? Okay, so what does this minus 7 indicates? Minus 7 indicates only 70% of the power is transmitted and only 30% is reflected back. Can we consider that case? No, we don't consider. Okay, so what is the preferable case? 90%, whatever the input power, you have provided at port 1, 90% should radiate and only 10%. So in that case, we are getting minus 10 dB. So what does this 0 dB indicates? 0 dB means in this formula, whatever the power you have provided, all the power without radiating, it is again coming back at same port. Okay, so what does this minus 15 indicates? Minus 15 indicates a better one. Minus 15 means 93% of the power is radiated and only 7% of the power is reflected back. What is this minus 20 indicates? 96% of the power is radiated, only 10% of the power is reflected back. So this minus 10 or minus 15 or minus 20 or minus 30, that is the better one. Better the antenna is. So in this diagram, let us see here how to very important if we observe any generals. Okay, so this graph will be compulsorily available, which indicate at what frequency any particular antenna is operating. So let us consider this graph is called as return loss graph, frequency versus return loss graph. This graph is frequency versus return loss. Okay, so on the x-axis generally, since all the microstrip patch antennas operates for higher frequency, the units are there, their units are in gigahertz. Okay, so compulsorily this minus 10 dB line you want to keep in mind. Okay, so for example, at what, if you observe this figure, at what frequencies this particular graph, by seeing this graph, you should come to know at what frequencies it is operating. So see here, from here to here means your antenna is not working, your antenna is not operating from 1 to 1.6 gigahertz. But where it is operating? It is operating here. Means whenever the values come less than minus 10 dB means this point. So this point means it is almost equal to 1.8 gigahertz. It is equal to the 1.8 gigahertz. Its value is equal to 1.8 gigahertz. So it is operating at 1.8 gigahertz. 1.8 gigahertz. And similarly, again it is going up to means in between this frequency, it is not operating. Again, where it is operating? It is operating at this point means this is nothing but 3.5 gigahertz. The second operating frequency is 3.5 gigahertz. Okay. Where again it is operating? From here to here it is not operating. So it is again operating at 5.5 gigahertz. Means a single antenna is operating at 3 frequencies here. What are the 3 frequencies? Why you are saying particularly these 3 frequencies? Because only this curve is coming less than minus 10 dB. Okay, less than minus 10 dB. So minus 10 dB or minus 15 dB or minus 20 dB, that are the better ones. Okay, but the threshold is minus 10 dB. Only here it is getting less than minus. So at this frequencies, the antenna doesn't operate. So based on this diagram, at what frequencies this antenna is supposed to operate? It is operating at 3 frequencies. The first one is 1.8 gigahertz. Second one is 3.5 gigahertz. And the third one is 5.5 gigahertz. So this antenna generally, if this type of results you are getting means this comes under multi-band antenna. This comes under multi-band antenna. So what is meant by this multi-band antenna? An antenna which operates for multiple applications or which operates at different frequencies. Here in the antenna terminology, I have already told that application means frequency. Here it is operating at 3 different frequencies. For example, if you observe here 3.5 gigahertz means what is the application? 3.5 gigahertz means Wi-Fi application. What is this 5.5 gigahertz? 5.5 gigahertz means nothing but it is WiMAX application. So a single antenna operating at 3 different frequencies. So the threshold is you want to consider it as minus 10. You want to consider it as minus 10. You want to consider it as minus 10. Okay. So now let us see the next one in this graph. So this graph. Okay. Now tell me from which frequency to which frequency it is operating. Okay. So if you observe here, from here to here, since the value minus 10 dB above, the antenna is not operating. It is not operating. Okay, so from which frequency to from which frequency it is operating? It is operating from, so first of all, you want to draw a line at minus 10 dB line. Minus 10 dB line. Okay, so it is operating from this frequency to this frequency. Okay, so what is this frequency? This frequency means on the x-axis we are having frequency. On the x-axis we are having frequency. So this is almost 3.5 gigahertz and this is 11.5, means this antenna is operating from 3.5 gigahertz to 11.5 gigahertz. If you observe, what is the difference between this graph and this graph? So this graph, this one comes under multi-band antenna. What about this one? So this antenna is operating from 3.5 gigahertz to 11.5. So see here, it is going up to minus 40, minus 50, means from here to here, the antenna is working. So this comes under wideband antenna. Wideband antenna. This graph represents wideband antenna or ultra wideband antenna, UWB or wideband. So what is meant by a wideband antenna? An antenna which operates for a wide range of frequencies. A wide range of frequency means the graph is getting below minus 10 dB from 3.5 gigahertz to 11.5 gigahertz. 11.5 gigahertz. So this comes under wideband antenna. It comes under wideband antenna. Okay, so it is operating from 3.0 gigahertz to 11.5 gigahertz. Okay, so this is a written loss in every paper, in every journal. Okay, so this is the one you want to keep in mind regarding microstrip patent now. So this graph is frequency versus written loss, frequency versus written loss. Okay, the first one is multi-band, which operates at only some particular frequencies. The second one is wide band, where it is operating for wide range of frequencies, where it is operating for wide range of frequencies, wide range of frequencies. Okay, so other parameter, very other important parameter. The first one we have already completed, the written loss. So now you come to picture, you are able to understand what is meant by the written loss. The second thing you'll see in any general or microstrip antenna, that is impedance bandwidth. Okay, is the bandwidth ordinary bandwidth what you see in the CE amplifier, AC DC bandwidth is same as the impedance bandwidth? No, a small difference is there. Okay, so how to calculate the bandwidth in general? For example, if you take CE amplifier, okay, so the graph will be like this. Let minus 3 dB, you will take minus 3 dB. Okay, so you will take, this is F high and FL. So this is F2 or F1. So how can you calculate in general CE amplifier or AC DC bandwidth? So it is nothing but higher frequency minus lower frequency bandwidth. Okay, but this is not same in the antenna terminology. Here we are going to use the parameter called as impedance bandwidth. Impedance bandwidth. What is meant by this impedance bandwidth? So see here, let us see here impedance bandwidth. How to calculate this impedance bandwidth? Okay, so this is, let us consider this is a graph between frequency versus written loss. Frequency versus written loss. So written loss means on the x-axis we will have frequency. Let us consider. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so similarly here a written loss on the y-axis, it is S11 in dB. So on the y-axis, okay. So this is 0 dB, this is minus 10 dB, this is minus 20 dB, this is minus 10 dB. So what I have told, what is the threshold you want to consider? You want to consider threshold as minus 10. So draw a line like this. Okay. So for example, for one particular antenna, if the graph is like this, if the graph is like this, the graph is like this. Okay, so if the graph is like this. Okay, so now tell me at how many bands it is operating, at what frequency it is operating. So no doubt. Okay, so you want to take this tip, you want to take this tip. Okay, so what is this value? This tip value, this tip value is nothing but 4.4 gigahertz. 4.4 gigahertz. So how to calculate the impedance bandwidth for this graph? So no doubt it is operating at only one frequency, that is at 4.4 gigahertz. So how to calculate this? Okay. So now see here in this graph, it is crossing this minus 10 dB at this point. Okay, so it is crossing minus 10 dB at this point. Consider this is F1 and it is leaving here, this is F2. Okay, now by seeing this graph, what are the values of F1 and F2? So what are the values of F1 and F2? By seeing this graph, the values of F1 and F2 are the values of F1. So the values of F1. So F1 value is 3.5 gigahertz and F2 value is 5.2 gigahertz. Okay, so how to calculate the impedance bandwidth? How to calculate the impedance bandwidth? So the impedance bandwidth is represented with percentage. So the formula is F2 minus F1 by FR into 100. So what is the value of FR? The value of FR is equal to F1 plus F2 by 2. The value of FR is equal to F1 plus F2 by 2. So, okay, tell me here, How to calculate this? What is the value of F1 and F2? So the value of F2 is 5.2 gigahertz minus 3.5 gigahertz by, what is the value of F4? F1 plus F2 by 2. So its value is 3.5 plus 5.2 by 2 into 100. Okay. So whatever the value you are getting, okay. So for example, maybe 10 or whatever the value. So this is how we can calculate the impedance bandwidth. This is also present in the generals. Okay. So this is the other important parameter you want to keep in mind while we are going to discuss regarding the microstrip patch antenna. So first one is return loss, second one is impedance bandwidth. So this is impedance bandwidth. Okay, so where what are this F1 and F2 on the upper and lower cutoff frequencies where the return loss reaches minus 10 dB, where the return loss reaches minus 10 dB. So this is F1, this is F2. Okay. So this is how we can calculate the impedance bandwidth. Okay, so let us discuss another parameter, that is voltage wave standing ratio. Voltage wave standing ratio. So the voltage wave standing ratio is defined as the ratio of maximum to minimum voltages of the antenna. Okay, so generally what is meant by standing wave? When a standing wave comes into picture, so let us take this is a one. This is a any conducting material. Okay, so this is any conducting material. So whenever you provided any input, okay, like this. Okay, so if there is any impedance mismatch, automatically the wave without propagating, it comes like this. So this is nothing but standing wave. Okay, this is nothing but standing wave. So the generally standing wave is the ratio of V max by V minimum. Okay, generally if you take different parameters are there. Okay, so standing wave is equal to V max by V minimum. Okay, so what is the range of standing wave or VSWR? The range. So you can define the VSWR in reflection coefficient also. It is 1 plus tau by 1 minus tau, where tau is the reflection coefficient. What is the value of tau? Reflection coefficient is ZL minus Z0 by ZL plus Z, where ZL is the load impedance and Z0 is the intrinsic impedance. Okay, so what is the range? Okay, so if you observe in this formula, so the range of VSWR you want to keep in mind, it is from 1 to infinity. Okay, so in this formula, compulsory the whatever may be the value of tau, the VSWR, the minimum value, the range is from 1 to infinity. So you want to keep in this mind. The range of VSWR is from 1 to infinity. So the range of VSWR is from 1 to infinity. The range of VSWR is from 1 to infinity. So similarly here, what are the things you want to keep in mind? So if the VSWR value, similarly, what you have seen in return loss, what is the threshold? Minus 10 dB. Here the VSWR value is in between 2 to 3. Okay, so any antenna at what frequencies its value is less than 2 or 3. Okay, so for example, let us consider this graph is between frequency versus VSWR, frequency versus VSWR, Okay, so let us consider this is frequency and this is VSWR. This is on the y-axis and this is on the x-axis. The frequency here that will be in gigahertz. Okay, so let us consider here. So this is 1, 2, 3, 4, 5, 6, 7. Okay, here the range of VSWR is from, it will start from, the range is from 1, okay, 2, 3, 4, 5. They may extend up to 10, 20 like this, or sometimes 200. So here you want to draw those. So here the minimum threshold is you want to take in between 2 and 3, means you can draw a line at 2. You can draw a line at 2 as we have drawn a line at minus 10 dB. So this is 2. This is 2. Okay. So this is 2. Okay. So in this 2, okay. So for example, let us consider for one antenna, if the graph is like this. Okay. Now tell me at what frequencies it is operating. Okay. So from here to here, the antenna is not operating. Okay. So where it reaches less than 2 means here, for example, here, what is the frequency here? It is 3 gigahertz. The first frequency is 3 gigahertz. Okay. So this is second one. The second one is 7 gigahertz. Okay. So the graph which comes below 2, the graph which comes below 2, only at that frequency we will consider it is operating at that particular frequency. So from this graph, this antenna is operating at 3 gigahertz and 7 gigahertz. So it is operating at 2 frequencies. It is operating at 2 frequencies. Okay. So this graph also present in any general which is related to microstrip pattern. This is also very, very important parameter. Okay. So let us see this graph. Tell me at what frequency it is operating. So no doubt you want to simply draw the minus 2 2 at 2 we want to draw the line. Okay. So the range is from 1 to infinity. So it is exactly operating at 2.45. So 2.4 is almost Bluetooth application. Okay. So it is operating at only one frequency. Okay. Let us take this graph. Okay. So this is for a single band. This is for single band. Okay. Now tell me in this band. Okay. So your first thing is, and now we have seen the graph, you have to draw a line at 2 dB. Okay. 2 dB. Okay. So if you observe here, from where to where this antenna is operating, the values are below 2. From which frequency? From this frequency to this frequency. From this frequency means this antenna is operating from 2.7 gigahertz to almost, what is this value? This value is almost 10.8 gigahertz. Okay, so this comes under wideband. This comes under wideband. This comes under multiband. Okay, so this comes under single band. Okay, so what is the value you want to consider? 2. Okay, so 2. So the values which are below 2. Okay, 1 to 2, that we will consider at that frequency only the antenna is operating. So from here to here, the antenna at for this frequencies, for this frequencies, the antenna is not working. Okay, from here only, from this frequency to this frequency. So this comes under wideband antenna. This comes under multiband because from here to here the antenna is not working. Only at these 2 frequencies it is operating. Okay. So these are the some parameters that will come across in any regularly in all the generals or everywhere. These are the 3 parameters you want to consider. These are the 3 parameters you want to consider.